What if everything you thought you knew about reality was just the tip of an unimaginable iceberg? Picture this: somewhere beyond the 3 dimensions we see and touch, space twists into shapes we can't even draw, and time doesn't just move forward, but folds back on itself like a cosmic accordion. This isn't science fiction. It's the frontier of multidimensional space and time exploration, where the rules of physics, as we know them, start to unravel. Today, we're diving deep into 36 revolutionary concepts that will stretch your mind to its limits, ideas so profound they could rewrite our understanding of existence itself. From hidden dimensions curled tighter than a coiled spring to gravitational echoes that might reveal parallel universes, these aren't just theories, they're keys to unlocking the universe's best-kept secrets. Think about the last time you felt truly awestruck, maybe staring at a starry sky or watching a documentary about black holes. That sense of wonder is just the beginning. Because what if I told you there are places where time loops like a broken record, or that gravity might leak into our world from another dimension entirely? Scientists are now exploring possibilities that sound like they're ripped from the pages of a fantasy novel, yet they're grounded in cutting-edge mathematics and physics. These ideas don't just challenge textbooks, they invite us to rethink what's possible. Could alternate versions of ourselves be living in a shadow universe just out of reach? Might time travel not only be possible but inevitable under the right conditions? The answers lie in the strange, beautiful dance of higher dimensions, a realm where the familiar laws of nature bend and warp in ways that defy common sense. This journey isn't just for physicists or mathematicians. It's for anyone who's ever looked up at the night sky and wondered what's really out there. Whether you're a science enthusiast hungry for the latest discoveries or someone who simply loves to ponder life's biggest mysteries, these concepts will ignite your imagination like never before. We'll explore how black holes might be portals to other realities, why some scientists believe our universe is just one page in an infinite cosmic book, and whether time itself could be an illusion. Along the way, you'll encounter theories so groundbreaking they blur the line between science and philosophy. So buckle up, because by the end of this exploration, the words space and time will never mean the same thing to you again. The universe is far stranger, far more magnificent than we've ever dared to dream, and this is just the beginning. What if the world around us, the trees, the stars, even your own hands, aren't truly 3-dimensional objects, but just incredibly detailed projections, like shadows cast by a deeper, hidden reality? This is the heart of the holographic universe theory, a concept so radical it turns our understanding of existence inside out. Imagine the universe as a cosmic movie screen, where everything we experience is just a high-definition projection of information encoded on a distant 2-dimensional surface. It sounds like science fiction, but physicists like Leonard Susskind have spent decades working out the math to support this idea, and the implications are staggering. At the core of this theory is a strange connection between black holes and information. When matter falls into a black hole, it doesn't just vanish. It leaves an imprint on the event horizon, the point of no return, like data etched onto a celestial hard drive. This discovery led scientists to wonder, if a black hole's surface can store information about everything inside it, could our entire universe work the same way? The holographic principle suggests that the 3-dimensional reality we perceive might actually be a kind of illusion, with all the true data of existence written on a vast, unseen boundary at the edge of space. This idea doesn't just rewrite cosmology, it could solve some of physics' biggest puzzles. Take quantum entanglement, where particles millions of light years apart instantly influence each other as if space and time don't exist. If the universe is fundamentally two-dimensional, with our 3D world as a projection, that spooky connection might just be the system reading from the same hidden code. Even dark matter, the invisible glue holding galaxies together, could be a side effect of this deeper layer of reality, like glitches in the cosmic hologram revealing where the true machinery lies. String theory, one of the most ambitious frameworks in physics, fits eerily well with this picture. If the universe is made of tiny, vibrating strings, their interactions could be the source code behind the hologram, generating everything from gravity to light. It's as if reality is a grand symphony, and we're only hearing one note, while the full composition plays out in dimensions we can't perceive. The holographic universe theory forces us to ask, if our world is a projection, what's casting the light, who or what is running the simulation? While we don't have answers yet, the mere possibility reshapes how we see everything from the quantum realm to the vast emptiness between galaxies. It's a reminder that the universe has always been stranger than we imagined, and the next great discovery might not be a new particle or force, but the realization that we've been reading reality's blueprint upside down all along. Time has always felt like the most relentless force in the universe, ticking forward without pause, dragging us from past to future in a straight, unbreakable line. But what if that's just an illusion? Einstein shattered the idea of time as a universal constant when he revealed it bends and stretches like taffy near massive objects like black holes. Yet even that might be just the first clue to something far stranger. Imagine time not as an arrow but as a river, twisting into eddies where it loops back on itself, or splitting into tributaries where every possible outcome plays out simultaneously. This isn't fantasy, it's the cutting edge of physics where experiments are revealing time's true fluid nature. Take atomic clocks placed on airplanes which tick ever so slightly faster than those on the ground. It's not just altitude affecting them, it's time itself flowing differently under weaker gravity, proving Einstein right. But quantum mechanics adds another layer of weirdness. Particles at the smallest scales seem to remember future events, reacting to measurements before they happen in ways that defy classical logic. Some scientists interpret this as evidence that time might not have a fixed direction at all, that past, present, and future could coexist in a vast, interwoven tapestry. Then there's the mind-bending idea of retrocausality, where effects might precede their causes. In quantum experiments, particles appear to make decisions based on future conditions, as if time's flow is negotiable. If this holds, it could mean the universe isn't just deterministic but participatory, with our observations shaping reality backward and forward. The implications for free will are staggering. If the future can influence the past, is our sense of choice just a side effect of time's flexibility? And what about time travel? If time forks like branches on a tree, as some multiverse theories suggest, then every decision might spawn parallel timelines where alternate versions of us live out every possible outcome. Black holes could be natural time machines, their extreme gravity twisting space-time into loops where you might return to your own past. Wormholes, hypothetical tunnels through space-time, could connect distant moments as easily as they connect distant places. The catch, surviving the journey would require physics we're only beginning to imagine. The most radical proposals come from theories like loop quantum gravity, where time itself might emerge from something deeper, a timeless sea of quantum relationships. In this view, the flow of time could be like watching a movie frame by frame, an illusion created by our limited perspective. If true, then the past isn't gone and the future isn't unwritten. They're all out there, part of a vast, dynamic structure we're only starting to map. So the next time you check your watch, remember, those seconds might not be slipping away. They could be bending, folding, or even doubling back. Time isn't just a backdrop to the universe, it's an active player, and we're only beginning to learn its rules. Whether it's a river, a fabric, or something beyond metaphor, one thing's certain: the clock in your hand is telling a story far more complex than it seems. The idea that our universe might be just one tiny bubble in an endless cosmic froth of realities is both exhilarating and humbling. Picture an ocean where each wave cresting on the surface is its own self-contained universe, with its own unique laws of physics, some where gravity is stronger, others where time runs backward, or where life as we know it could never exist. This is the Multiverse Hypothesis, a vision of reality so vast it makes our observable cosmos feel like a single grain of sand on an infinite beach. One of the most compelling versions of this theory comes from inflationary cosmology, which suggests that right after the Big Bang, space expanded faster than light itself, stretching quantum fluctuations into entire universes. Think of it like blowing up a balloon covered in tiny dots. Each dot grows into its own separate world, forever drifting apart. But here's where it gets wild. Some physicists propose these bubble universes might occasionally collide, leaving behind cosmic scars in the form of strange temperature variations in the cosmic microwave background, the afterglow of the Big Bang. Imagine finding a fingerprint on your window, except the window is the sky, and the fingerprint is evidence of another universe brushing against ours. Then there's the many worlds interpretation of quantum mechanics, which takes the multiverse idea even further. Every time a quantum particle faces a choice, like whether to spin left or right, the universe splits, creating alternate timelines where every possible outcome plays out. In one world, you took that job overseas. In another, you stayed home. Somewhere out there, dinosaurs might still rule the Earth, or the Roman Empire never fell. It's not science fiction, it's a serious proposal to explain why quantum particles behave so unpredictably. The catch: these parallel worlds would be forever out of reach, hidden behind the veil of quantum decoherence, like radio stations tuned to frequencies we can't access. But how could we ever prove any of this? Some researchers scour the cosmic microwave background for anomalous patterns, circular bruises in the fabric of space that could mark a collision with another universe. Others look for deviations in the fundamental constants of nature, like the strength of gravity or the mass of electrons, which might vary from bubble to bubble. So far, the evidence is elusive, but the search itself reshapes how we think about reality. If our universe is just one of countless others, it forces us to ask, are the laws of physics fine-tuned for life, or is life just a lucky accident in a cosmic lottery where most tickets are duds? The multiverse also stirs philosophical whirlwinds. Take quantum immortality, the eerie idea that in some branch of the multiverse, you never die because there's always a timeline where you survive. Or ponder destiny. If every choice spawns new worlds, does free will mean anything, or are all versions of you equally real? These questions blur the line between physics and metaphysics, challenging us to rethink what it means to exist. Whether the multiverse is real or not, the mere possibility cracks open a door to a reality far grander than we ever dreamed. It suggests that our universe, with its galaxies and black holes and fleeting human lives, might be just one note in an infinite symphony of existence, a symphony we're only beginning to hear. Wormholes sound like something straight out of a sci-fi blockbuster, cosmic tunnels burrowing through the fabric of space-time, connecting distant corners of the universe in the blink of an eye. But here's the twist: they weren't dreamed up by Hollywood. The idea traces back to Albert Einstein and his colleague Nathan Rosen, who discovered that the equations of general relativity allow for bizarre shortcuts through the cosmos. Picture space-time as a sheet of paper folded in half. A wormhole would be like poking a pencil through both layers, creating a bridge between points that would otherwise take eons to reach. The catch, these Einstein-Rosen bridges, as they're formally called, are so unstable that most theoretical models show them snapping shut the instant anything tries to pass through. So how could we ever keep one open long enough to step inside? That's where exotic matter comes in, a hypothetical substance with negative energy density that could theoretically prop a wormhole's throat open like cosmic scaffolding. Imagine trying to hold a vacuum tunnel open against the crushing force of gravity. Exotic matter would act as the ultimate counterweight, resisting collapse. The problem, we've never observed such material in nature, and creating it would require energies far beyond our current technology, possibly even harnessing the power of entire stars. Some theories suggest quantum effects near black holes might naturally spawn microscopic wormholes, but scaling them up for human travel is another universe of challenges. Then there's the paradox problem. If wormholes enable time travel, as some solutions to Einstein's equations suggest, they could unravel causality itself. Take the infamous grandfather paradox. What if you traveled back and accidentally prevented your own birth? Physics has a few wild answers. Maybe the universe enforces consistency, bending events to ensure you couldn't actually change the past. Or perhaps every attempt to alter history just spawns a new branch of the multiverse, leaving the original timeline untouched. These aren't just thought experiments. They're clues that wormholes, if real, would rewrite the rules of reality in ways we're only beginning to grasp. Could wormholes ever be more than mathematical curiosities? Breakthroughs in quantum gravity research hint at possibilities. If space-time is fundamentally woven from entangled quantum threads, as some theories propose, then wormholes might be the natural seams where those threads knot together. Advanced civilizations millions of years ahead of us might already be using them as interstellar highways. For now, they remain tantalizing what-ifs, but the sheer fact that they emerge from solid physics means we can't dismiss them as fantasy. After all, black holes were once considered too strange to exist until we found them lurking in the heart of nearly every galaxy. Wormholes might just be the next great cosmic surprise, waiting for the right moment to reveal themselves. The deeper we dig into these ideas, the clearer it becomes. The universe doesn't just allow for the extraordinary, it seems to demand it. Whether wormholes remain locked in equations or one day become our gateway to the stars, they remind us that space-time is far more malleable, far more mysterious than we ever imagined. And that's the real thrill, not just the answers we might find, but the questions we've yet to ask. Imagine two coins flipped simultaneously on opposite sides of the galaxy, yet no matter how far apart they are, they always land on the same side. That's the essence of quantum entanglement, one of the most baffling and beautiful phenomena in physics. When particles become entangled, they share a mysterious connection that defies distance. Change the spin of one electron here, and its partner light years away instantly mirrors that change, as if space between them doesn't exist. Einstein famously dismissed this as spooky action at a distance, convinced it revealed a flaw in quantum theory. But decades of experiments, from photon pairs split in labs to satellites beaming entangled particles across continents, have proven him wrong. The universe really does work this way, and the implications are staggering. So how does this spookiness actually happen? Think of entanglement not as a signal traveling faster than light, but as two pages of the same book. Tear them apart, and they're still part of the same story. Edit one, and the other updates instantly because they were never truly separate to begin with. This challenges our deepest assumptions about locality. the idea that objects are only influenced by their immediate surroundings. Quantum entanglement suggests that at some fundamental level, everything might be interconnected in ways we can't yet see. Some theorists propose this could hint at extra dimensions, where particles remain linked through higher spatial folds invisible to us. Others wonder if entanglement reveals a hidden cosmic code, a quantum internet woven into the fabric of space-time itself. The practical possibilities are just as mind-bending. Could we use entangled particles to build unhackable quantum networks where information leaps securely across the globe? Experiments with quantum cryptography are already testing this, creating communication channels where any eavesdropping would immediately break the entanglement, alerting both sender and receiver. Even wilder is the notion of quantum teleportation, not beaming objects like in sci-fi, but transmitting the exact quantum state of a particle from one location to another without crossing the space in between. In 2017, Chinese scientists teleported a photon from Earth to a satellite orbiting 300 miles overhead, proving the concept isn't just theoretical. But the deepest mystery remains: what's really mediating this instantaneous connection? One radical idea is that entangled particles aren't communicating at all. They're accessing a deeper layer of reality where time and space emerge from something more primitive, like pixels on a screen drawing from the same source code. If true, entanglement might be a glimpse behind the curtain, showing us the universe's true operating system. From black holes to the birth of the cosmos, this phenomenon could be the key to unlocking secrets we've barely begun to fathom. So the next time you feel alone, remember at the quantum level, everything is far more connected than it seems. What if the universe isn't just governed by laws of physics but by lines of code? The simulation hypothesis flips our understanding of reality on its head, proposing that everything, from the stars to your morning coffee, might be an elaborate digital construct, a cosmic virtual reality running on some advanced civilization supercomputer. Philosopher Nick Bostrom laid out a chillingly logical case for this. If future civilizations could create hyper-realistic ancestor simulations, and if they had any desire to do so, the sheer number of simulated minds would vastly outnumber biological ones. Statistically speaking, you're more likely to be one of those simulations than an organic original. But how would we even begin to test such a radical idea? Some researchers point to potential glitches in the system, oddities that feel like bugs in the cosmic software. Take quantum indeterminacy, where particles exist in multiple states until observed. Could this be the universe's way of optimizing processing power, only rendering details when necessary, like a video game loading graphics as you explore? Then there's the Mandela effect, where large groups misremember events identically, like the false collective memory of Nelson Mandela dying in prison. Could these be patches or updates in the simulation, altering shared history without perfect backward compatibility? Even the fundamental limits of our universe might hint at artificial constraints. The speed of light, nature's ultimate speed limit, could be a processing cap, preventing the simulation from overloading. The Planck length, the smallest measurable unit of space, might be the pixel size of reality's resolution. And dark energy's mysterious acceleration of the universe's expansion, that could be the system's memory allocation expanding to accommodate new data. The real mind-bender comes when we ask who's running the simulation and whether we could ever interact with them. Some theorists suggest that if our creators exist in a higher dimensional base reality, they might not even perceive us as conscious beings, any more than we notice individual pixels on a screen. Others propose that glitches like déjà vu or unexplained cosmic anomalies could be intentional Easter eggs left by programmers to nudge us toward questioning our reality. But here's the twist: if we're in a simulation, hacking it might not be science fiction. Quantum experiments manipulating particles at a distance could be early attempts to tickle the code, probing the boundaries of the simulation's rules. If consciousness itself is part of the program, meditation or psychedelics might offer ways to glimpse the source, like a character in a game becoming aware of the keyboard controlling it. Whether the simulation hypothesis is profound truth or provocative thought experiment, it forces us to confront the nature of existence itself. If reality is code, then the universe isn't just stranger than we imagine. It might be stranger than we can imagine, a labyrinth of nested simulations where every answer reveals deeper layers of mystery. And that's the real power of this idea, not just to explain our world, but to expand what we believe is possible. Dark matter is the universe's ultimate ghost story, an invisible force sculpting galaxies, bending light, and holding the cosmos together, yet slipping through our detectors like a shadow through a sieve. We know it's there because its gravitational grip keeps stars from flying apart. But what if the reason we can't see or touch it isn't just because it's dark, but because it exists partially in dimensions beyond our own? Imagine a creature living on a flat sheet of paper, unaware of the world above and below it. If you reached down and poked the paper, the creature would see only a mysterious, unexplained force, just like we perceive dark matter's gravity without sensing its full form. String theory offers a tantalizing clue. In a universe with extra-spatial dimensions curled up smaller than an atom, particles of dark matter might be vibrations of cosmic strings that extend into these hidden realms. Picture a guitar string vibrating in 3 dimensions. Now imagine plucking one that resonates in 6 or 7. The higher dimensional notes would be imperceptible to us, yet their gravitational echoes could ripple into our world, manifesting as the missing mass we call dark matter. This isn't pure speculation. Equations suggest certain string vibrations, called sterile neutrinos, could match dark matter's elusive properties, rarely interacting with ordinary matter except through gravity. Scientists are hunting these phantoms with tools stranger than fiction. Deep underground, where Earth's crust shields detectors from cosmic noise, experiments like Xeno-NNT and LUX Zeppelin wait for a single atom to recoil, a potential collision with a dark matter particle. Others, like the Ice Cube Neutrino Observatory in Antarctica, monitor vast arrays of sensors frozen in glacial ice, hoping to catch a flicker of energy from a dark matter annihilation. Even space telescopes like the James Webb peer into galactic collisions, mapping how dark matter's gravity bends light like a cosmic lens, revealing its hidden structure. The boldest idea, that dark matter isn't just hiding in extra dimensions, it might be the glue binding them together. Some models propose that what we perceive as dark matter's pull could actually be the tension of higher dimensional space itself, stretching and warping the fabric of our universe from the outside. If true, then finding dark matter wouldn't just solve a cosmic mystery, it would crack open a doorway to dimensions we've never seen, proving that reality is far grander than the stage we currently inhabit. Every galaxy, every star, every atom we know might be floating on the surface of something deeper, something vast, something waiting to be discovered. The race to unmask dark matter isn't just about filling in a gap in our equations. It's a quest to answer one of humanity's oldest questions: what is the universe really made of? And the answer might not lie in the particles we can see, but in the hidden dimensions we're only beginning to imagine. Here's a chilling possibility. What if you reading these words right now aren't the product of billions of years of evolution on a rocky planet, but instead a momentary flicker of self-awareness, conjured into existence by pure chance in the cold, empty void of space? This is the Boltzmann brain paradox, a thought experiment so unsettling it makes the simulation hypothesis seem almost comforting. Named after physicist Ludwig Boltzmann, who first grappled with the statistical nature of reality, the idea hinges on a simple but profound question. In an infinite universe where entropy dictates disorder, could random quantum fluctuations spontaneously assemble a fully formed, conscious mind complete with false memories of a life it never lived? Think of it like shaking a box of alphabet soup for eternity. Eventually, the letters might randomly spell out war and peace, not because Tolstoy was involved, but simply because given enough time, even the most improbable configurations become inevitable. Now scale that up to the cosmos. Given infinite time and space, quantum jitters could theoretically arrange particles into a self-aware brain, complete with the illusion of a past, a body, even a universe around it. The kicker, statistically, such isolated Boltzmann brains would vastly outnumber ordinary, biologically evolved minds like ours. So why do we find ourselves embedded in a coherent 8 billion-year-old universe instead of drifting alone in the abyss? Some physicists dismiss this as a philosophical curiosity, but the paradox has teeth. It exposes a glaring tension between cosmology and quantum mechanics. If our standard model of the universe's origins is correct, a hot Big Bang followed by accelerating expansion, then given enough time, random fluctuations should produce Boltzmann brains far more often than real planet-bound observers. The fact that we don't experience this might mean our theories are incomplete. Maybe the universe isn't infinite. Maybe consciousness requires more than just particle arrangements. Or perhaps, as some quantum interpretations suggest, observation itself collapses reality into stable, consistent states, preventing such freak occurrences. The implications spiral into existential vertigo. If Boltzmann brains are possible, how could you ever prove you're not one? Your memories, your sense of continuity, even the laws of physics you rely on could be a fleeting hallucination, vanishing as quickly as it appeared. This isn't just solipsism, it's a mathematical challenge to the foundations of reality testing. Scientists like Sean Carroll argue that the paradox forces us to refine our models, perhaps pointing toward a deeper understanding of how time, entropy, and observation intertwine. Yet there's a strange beauty here too. The Boltzmann brain scenario isn't just about doubt, it's about the fragility of existence. It reminds us that consciousness, whether born in a star-lit cradle or a quantum accident, is a miracle, one we're still learning how to measure. So the next time you gaze at the night sky, consider this. The very act of questioning your place in the cosmos might be the strongest evidence that you're not just a ghost in the quantum machine, but part of something far more enduring. The universe, after all, seems to prefer stories to statistical noise, and yours is still being written. Imagine a snowflake that never melts, not because it's frozen in place, but because it constantly reforms itself in a never-ending dance, cycling through its crystalline patterns without ever losing energy. That's the essence of a time crystal, a bizarre form of matter that defies one of physics' most fundamental rules, the inevitability of equilibrium. Normally, everything in the universe tends toward a state of rest. Hot coffee cools, bouncing balls stop, even stars burn out. But time crystals break this mold. They're structures that oscillate, repeat, and tick like cosmic clocks without any energy input, existing in a perpetual cycle of motion that seems to thumb its nose at entropy itself. The idea was first proposed in 2012 by Nobel laureate Frank Wilczek, who wondered, if ordinary crystals have atoms arranged in repeating spatial patterns, could there be matter that repeats in time instead? At first, many physicists dismissed it as impossible, a violation of thermodynamics. But by 2017, labs at Harvard and the University of Maryland had created time crystals using chains of ytterbium atoms and diamond impurities, chilling them near absolute zero and nudging them with precise laser pulses. The result, a system that flipped between two states indefinitely, like a pendulum swinging forever without friction, its rhythm locked not by external forces but by the crystal's own quantum structure. What makes time crystals so revolutionary isn't just their defiance of equilibrium, it's what they reveal about the fabric of reality. They exist in a new phase of matter, one where time itself becomes part of the material's architecture. Think of it like a river flowing upstream. The water isn't defying gravity, it's following a deeper, hidden current. Time crystals do something similar, tapping into quantum entanglement to sustain their motion. Each particle in the crystal is linked to every other, creating a network where changes ripple instantaneously, keeping the system forever out of sync with the outside world, a phenomenon called many-body localization. The practical implications are staggering. Quantum computers, which rely on fragile, entangled states, could use time crystals as ultra-stable frameworks for processing information. Picture a quantum bit that doesn't decohere. A time crystal's endless rhythm might lock data in place, shielding it from the noise that plagues current systems. Even more tantalizing is their potential to probe the boundaries of physics. Some theories suggest time crystals could simulate exotic states of matter predicted to exist inside neutron stars, or even help us test ideas about time's arrow, why we remember the past but not the future. But the deepest mystery remains: how far can this phenomenon scale? Could there be natural time crystals lurking in the cosmos, hidden in the quantum froth of space-time? If so, they'd challenge our understanding of how energy and order emerge in the universe. Time crystals don't just give us a new material to study, they offer a lens to examine the very nature of time, motion, and the invisible rules that stitch reality together. And that's the real magic, discovering that the universe still has phases of matter we've never dreamed of, waiting to rewrite the textbooks once again. Black holes don't just crush matter, they might erase the very information that defines it. And that's a problem that's been keeping physicists awake for decades. Picture this: you toss a book into a fire, the pages burn, the ink fades, but in principle, if you could track every ash particle and wisp of smoke, you could reconstruct the book's contents. That's the cornerstone of quantum mechanics. Information is never truly lost, just scrambled. But black holes, they seem to break this rule. When something crosses the event horizon, it's not just torn apart by gravity. According to Stephen Hawking's groundbreaking work, the black hole slowly evaporates over eons, emitting faint radiation until it vanishes entirely. Here's the paradox: if the black hole disappears, what happens to all the information about the stars, planets, or spaceships it swallowed? Hawking initially thought it was gone forever, erased from the universe. That conclusion sent shockwaves through physics, because if information can vanish, the entire framework of quantum theory starts to unravel. The conflict boils down to a cosmic tug of war between general relativity and quantum mechanics. Relativity says black holes are simply defined only by their mass, spin, and charge, with no memory of what fell in. Quantum mechanics insists every particle carries information that can't be destroyed. So who's right? One radical solution is the firewall hypothesis. Imagine the event horizon isn't just an invisible boundary, but a searing wall of energy that incinerates anything approaching it. This would preserve information by preventing it from ever entering the black hole, but it's a violent fix that contradicts Einstein's prediction of an uneventful crossing. Another approach leans on holography, the idea that all the information inside a black hole is actually encoded on its surface, like a cosmic QR code. When the black hole evaporates, that data isn't lost. It's imprinted on the Hawking radiation, leaking out in subtle patterns we might one day decode. Recent breakthroughs have added even wilder twists. Some theorists suggest black holes aren't the end but a gateway, with information funneled into baby universes budding inside them. Others propose that entanglement, the same quantum glue linking particles across space, might tether what falls in to what radiates out, creating a hidden quantum circuit that preserves information in ways we can't yet measure. The stakes couldn't be higher. If information isn't lost, it implies black holes are the universe's ultimate archivists, not destroyers. And if it is, then our understanding of reality is missing something profound, a shadow layer of physics where the rules we trust don't apply. This isn't just academic wrestling, it's a quest to answer whether the universe forgets. Every experiment, every equation nudges us closer to knowing if black holes are cosmic shredders or the most sophisticated storage devices in existence. The answer could rewrite not just astrophysics, but the very meaning of existence itself, because if information shapes reality, then black holes might hold the key to how the universe remembers its own story. The Big Bang wasn't the beginning. It might have been the cosmic equivalent of a car crash. That's the startling premise of the EPR Universe theory, which reimagines our origins not as a fiery singularity, but as a collision between two vast, higher-dimensional membranes floating in a hidden expanse of reality. Picture two sheets of paper drifting through a breeze, slowly drawing closer until they smack together with enough force to ignite an entire universe in the space between them. These aren't just any sheets, they're brains, shorthand for membranes, theoretical structures predicted by string theory that could stretch across dimensions beyond our perception. When they collide, the energy released doesn't just spark stars and galaxies. It resets the cosmic clock, kicking off a new cycle of expansion we now call the Big Bang. This model solves one of cosmology's biggest headaches, the singularity problem. Traditional Big Bang theory points to an infinitely dense, infinitely hot starting point where physics as we know it breaks down. But in the ekpyrotic scenario, there's no singularity, just a transfer of energy between brains, like a cosmic game of hot potato. The universe doesn't emerge from nothing. It recycles, with each collision birthing a new epoch while preserving traces of the old. It's a vision of eternity where the cosmos breathes in and out, expanding after each collision, then contracting over trillions of years until the next impact. How does this stack up against inflation, the reigning champion of cosmic origins? Inflation posits that the universe underwent a fleeting, faster-than-light expansion right after the Big Bang, smoothing out wrinkles in space-time and explaining why the cosmos looks so uniform. The ekpyrotic model achieves similar uniformity, but without requiring that explosive growth spurt. Instead, the brains approach each other slowly, their interaction stretching space-time flat over eons, like rolling out dough with infinite patience. The difference, inflation, is a one-time event, while ekpyrosis suggests we're living in just one chapter of an endless cosmic saga. The most tantalizing question isn't just about the past, it's about evidence. If our universe was forged in a brain collision, could the shockwaves have left fingerprints in the cosmic microwave background, that faint glow from the universe's infancy? Some researchers speculate that certain anomalous patterns in the CMB, like cold spots or unusual alignment, might be cosmic bruises from the impact. Others hunt for gravitational waves from the event, though these would be far older and fainter than any we've detected so far. Even the distribution of dark matter could hold clues, as brain collisions might scatter it in telltale ways we're only beginning to model. What's truly mind-bending is the implication of cyclicity. If the ekpyrotic model is right, then every particle in your body, every star in the sky, is part of a cycle older than time itself. The universe didn't just begin, it rebooted, carrying forward quantum information from a previous iteration like a cosmic baton pass. It's a humbling thought. The atoms in your hands might have witnessed countless big bangs, each collision writing a new volume in a story with no first page and no final chapter. Whether this theory holds up or not, it reminds us that the universe's origins might be stranger, grander, and more interconnected than we ever dared to dream. The silence of the cosmos is deafening. With billions of galaxies, each home to countless stars and planets, the universe should be teeming with civilizations, yet our radios and telescopes hear nothing but static. This eerie quiet is the heart of the Fermi paradox, the glaring contradiction between the high probability of alien life and the total lack of evidence for it. But what if we've been looking in the wrong places or the wrong dimensions? One radical solution suggests advanced civilizations might be operating in higher spatial dimensions, their activities as invisible to us as a shadow is to a fish. Imagine ants crawling on a tabletop, unaware of the human hand reaching toward them from above. To the ants, the hand appears suddenly, defying their two-dimensional logic. Similarly, a fourth-dimensional civilization could observe or even manipulate our world without leaving traces we'd recognize. Their technology wouldn't just surpass ours, it would be fundamentally incomprehensible, like explaining Wi-Fi to medieval peasants. Then there's the zoo hypothesis, the idea that Earth is intentionally isolated, a cosmic wildlife preserve where advanced societies observe us from a distance, enforcing a galactic prime directive to avoid interference. It's a chilling thought. What if humanity's struggles, triumphs, and wars are nothing more than entertainment for unseen spectators? Proponents point to oddities like UFO sightings as potential leaks in the containment, though skeptics argue these are more likely misidentified natural phenomena or human-made craft. But darker explanations loom. The Great Filter theory suggests that some catastrophic barrier, nuclear war, runaway AI, or environmental collapse wipes out civilizations before they can colonize the stars. The haunting question isn't just whether the filter lies ahead of us, but whether we've already passed it. If life is common but intelligence is a fatal flaw, then the silence isn't mysterious, it's a warning. Yet the most unsettling possibility remains that we're utterly alone. The conditions for life might be rarer than we think, or consciousness could be a freak accident in a universe built for rocks and plasma. Either answer reshapes our place in the cosmos. Are we pioneers, prisoners, or cosmic orphans? Until we hear otherwise, the stars keep their secrets, and the paradox grows louder with every empty scan of the sky. Right now, an invisible force is stretching the universe apart at an ever-increasing rate. Dark energy, the mysterious substance making up 68% of the cosmos. But what if this isn't just a gentle push? What if it's a countdown to the most violent end imaginable, the Big Rip? A cosmic doomsday where dark energy grows so strong it shreds galaxies, tears atoms apart, and even rips the fabric of space-time itself. Picture a rubber band stretched tighter and tighter until it snaps. Now imagine that rubber band is reality. This isn't just theoretical. If dark energy's strength isn't constant but instead grows over time, a form called phantom energy, it could eventually overpower every force in nature, from gravity to the bonds holding your very molecules together. Here's how it would unfold. First, galaxy clusters would fly apart as the space between them expands faster than light can bridge the gap. Next, individual galaxies would disintegrate, stars ripped from their orbits like beads scattering from a broken necklace. Then catastrophe would reach planetary scales. Earth would explode as the phantom energy surging through space overwhelms gravity's grip. Finally, in the last microseconds, atoms themselves would be torn asunder, protons and electrons ripped apart by the stretching of space itself. Even time could fracture, the universe's final moments playing out in frozen, disconnected instants. But why would dark energy behave this way? Some theorists propose a spine-chilling explanation. We're detecting energy leaking into our universe from higher dimensions. Imagine a bucket with tiny holes, water seeping in from an unseen source. If dark energy is really higher dimensional gravity dripping into our 3D world, its increasing strength might signal those dimensions collapsing or decaying, funneling more energy into our reality until it's overwhelmed. String theory models even suggest this could be tied to the landscape of possible universes. Ours might be unstable, destined to unravel as it slides into a lower energy state. Not everyone buys the apocalypse scenario, though. Critics point out that phantom energy requires dark energy's equation of state, a measure of its pressure and density, to cross a forbidden threshold called W equals -1. Current observations hover near that line but don't definitively cross it. Others argue the Big Rip contradicts quantum field theory, which suggests dark energy should remain constant, not self-reinforcing. There's also the eerie coincidence that we'd happen to live in the brief cosmic era, just before everything tears apart. Statistically unlikely, unless the universe is far younger or older than we think. Yet the mystery remains. If dark energy isn't phantom energy, why is the universe accelerating faster than predicted? Whether it heralds doom or just deeper physics, one thing's certain: the fate of the cosmos hinges on forces we're only beginning to understand. And that's the real lesson here. The universe doesn't owe us survival. Its rules are written in dimensions we can't see, playing out on timescales we can barely grasp. The Big Rip might be fiction, or it might be the last page in our story waiting to be turned. The act of looking at something seems simple until you peer into the quantum realm, where observation doesn't just record reality, it might create it. Picture a single electron zipping around an atom. Before you measure it, it exists in a blur of probabilities, a superposition of all possible positions. But the moment you detect it, that fuzzy cloud collapses into a single, definite location. This is the quantum observer effect, and it raises a question that's haunted physicists for a century. What exactly counts as an observer? Does it require a human mind, as pioneers like John von Neumann believed? Or is consciousness irrelevant, with measurement happening mechanically through detectors and particles? Von Neumann's bold hypothesis that the boundary between quantum possibilities and concrete reality lies in the human mind sounds like philosophy, but it emerged from hard math. In his view, the chain of quantum interactions, from particle to detector to scientist's brain, never truly resolves. The wave functions collapse until conscious awareness steps in. It's as if the universe hesitates, holding onto all possible outcomes until a sentient observer makes the final call. Nobel laureate Eugene Wigner took this further with his famous Wigner's friend thought experiment. If a scientist's friend performs a quantum measurement in a sealed lab, is the result still undetermined until Wigner himself opens the door and looks? If so, reality becomes a hall of mirrors dependent on who's watching. Modern physics offers less mystical but equally mind-bending alternatives. Decoherence theory, for instance, argues that collapse happens when quantum systems interact with their environment, no consciousness required. A photon hitting a camera sensor doesn't wait for a human to check the data. It chooses a state the instant it collides with matter. Yet even here, mysteries linger. Why does interaction appear to force a single outcome? Some interpretations, like the many worlds hypothesis, dodge the question entirely. Every possible outcome happens, branching into parallel realities where each version of you sees a different result. Then there's the quantum eraser experiment, which adds another layer of strangeness. Particles seem to decide their past behavior retroactively based on how they're observed later. It's as if the universe edits its own history to stay consistent with the present, a twist that makes von Neumann's consciousness-driven model feel almost tame by comparison. So where does this leave us? The truth might lie in the gap between math and intuition. Quantum mechanics works flawlessly as a predictive tool, but its rules clash with our everyday sense of reality. Whether consciousness plays a special role or not, one thing's clear. At the quantum level, the universe doesn't just feel participatory. It might require participation to exist at all. And that's the real shocker. The act of asking what's real could be the very thing that brings reality into focus. Black holes dominate the cosmic horror genre, inescapable voids where gravity wins forever. But what if there's a cosmic counterbalance, a celestial fire hose blasting matter and energy outward with equal ferocity? Enter white holes, the hypothetical twins of black holes, where the event horizon isn't a point of no return but a barrier nothing can cross from the outside. Picture a black hole running in reverse. Instead of collapsing into a singularity, a white hole would explode from one, violently ejecting everything in its path like a cosmic replay of the Big Bang. The math behind this symmetry is eerily elegant. Einstein's equations don't care if time flows forward or backward, they work just as well in reverse. Plug in negative time to a black hole solution and voila, you've got a white hole. Some theorists, like Carlo Rovelli, suggest that when a black hole dies, it might not vanish but rebound as a white hole, recycling its contents in a burst of new spacetime. The catch: this process would take billions of years longer than the current age of the universe, unless quantum gravity shortcuts the wait, turning microscopic black holes into fleeting white holes in lab experiments. The wildest idea that our entire universe is the aftermath of a white hole's eruption. The Big Bang's sudden explosion of energy matches a white hole's behavior so precisely that some physicists speculate we're living inside the remnants of one. It's a cosmic Russian doll. Our expanding universe could be the other side of a black hole from a parent cosmos, with every galaxy, every atom, born from an ancient singularity's refusal to stay silent. Wormholes add another twist. If a black hole and white hole are connected by an Einstein-Rosen bridge, the result isn't just a portal through space, it's a tunnel through time. Matter falling into the black hole could emerge from the white hole in another era, another universe, or even another timeline. The problem: these wormholes would be unstable, snapping shut faster than light can traverse them. Unless exotic matter holds them open or quantum effects stitch the tunnel's walls into something durable. So why haven't we seen white holes yet? They'd be spectacular, blazing with gamma rays as they vomit plasma at near light speed. One explanation: they're incredibly rare, appearing only in the universe's earliest moments. Another: they're hiding in plain sight. Some astrophysicists propose that fast radio bursts, those mysterious, milliseconds-long blasts of energy, could be white holes coughing up quantum information. Others suggest dark matter itself might be the ash of ancient white hole eruptions, a relic of cosmic recycling we're only now learning to read. Whether white holes are real or just mathematical phantoms, they force us to rethink the universe's balance sheet. If black holes are the universe's garbage disposals, white holes might be its fountains, proof that destruction and creation are two sides of the same coin. And that coin still spinning in the air, waiting to land. The human brain might be the most sophisticated holographic projector in existence, not just processing reality, but constructing it from scratch. If the universe itself operates like a cosmic hologram, as some physicists theorize, then our brains could be running the same software, encoding memories and perceptions in a non-local, distributed way. Imagine shining a laser through a shattered piece of stained glass. Even if you remove half the shards, the original image still emerges, just fainter. That's the essence of a hologram. Every fragment contains the whole. Neuroscientists like Carl Pribram proposed that our brains might store memories similarly, not in specific neurons, but in wave-like patterns spread across the entire cortex. Lose a chunk of brain tissue, and the memory persists, just degraded, like a hologram missing pieces. This idea could crack open some of consciousness's biggest mysteries. Take near-death experiences where people report vivid, life-spanning visions even when their brains show minimal activity. If memories aren't locked in synapses but etched into the brain's electromagnetic field, a kind of biohologram, then those recollections might persist briefly even after clinical death, like a projector's afterglow. Even telepathy, often dismissed as pseudoscience, gets a fresh look under this model. If two brains' holographic fields vibrate at compatible frequencies, could they momentarily sync, sharing information outside classical physics? It's a wild idea, but quantum entanglement proves particles can communicate instantaneously across space. Why not minds? Critics argue that holographic brain theory stretches analogy too far after all. Neurons aren't lasers, and synaptic pruning clearly disrupts memory. Yet experiments keep revealing oddities that fit the model. Rats with up to 90% of their visual cortex removed can still perform complex visual tasks, as if the information wasn't stored in the missing tissue at all. Meanwhile, EEG readings show that memories trigger brain-wide oscillations, not localized sparks. It's as if the brain broadcasts its data like a radio signal, with each neuron tuned to pick up certain frequencies. The implications ripple beyond biology. If consciousness is fundamentally holographic, it might explain why we perceive a seamless, three-dimensional world despite the brain's fragmented processing. Your experience of a sunset isn't stitched together from pixels. It's rendered all at once, like a hologram assembling light into a unified image. Some theorists even speculate that this could bridge neuroscience and quantum physics, suggesting the brain doesn't just perceive reality but participates in its creation, collapsing quantum possibilities into concrete experience. Whether the holographic brain holds up or not, it forces us to ask, is the mind a machine or a masterpiece of interference patterns, weaving reality from waves of potential? The answer might not lie in the gray matter under our skulls, but in the invisible, shimmering fields that dance within it, and perhaps beyond it. The dream of zipping between stars at faster than light speeds isn't just science fiction. It might be hiding in the fine print of Einstein's equations. Meet the Alcubierre warp drive, a theoretical concept so audacious it treats space-time like a cosmic escalator, carrying a ship forward while the fabric of the universe itself does the moving. Here's how it works. Instead of trying to push a vessel through space at impossible velocities, the drive would compress space-time in front of the ship and expand it behind, creating a warp bubble that rides the distortion like a surfer on a wave. Inside this bubble, the ship wouldn't move at all relative to its local space, meaning no relativistic time dilation, no infinite mass at light speed, and no violation of Einstein's cosmic speed limit. The universe would simply fold around it. Mexican physicist Miguel Alcubierre first crunched the numbers in 1994, showing that while the idea sounds fantastical, it's mathematically consistent with general relativity. But there's a catch big enough to swallow a star: the energy required. early estimates suggested you'd need the equivalent of Jupiter's mass converted entirely into energy, something even a Kardashev Type II civilization might struggle to muster. Then came a glimmer of hope. Later calculations tweaked the design, reducing the energy needs to just the mass of Voyager 1, though that's still far beyond our reach. The real kicker, you'd also need exotic matter with negative energy density, a substance that defies gravity, pushing space apart instead of pulling it together. We've never observed such matter in nature, though quantum mechanics allows for fleeting glimpses of it in phenomena like the Casimir effect, where empty space seethes with particle-antiparticle pairs that briefly exhibit negative energy. NASA Eagleworks Lab has dabbled with tabletop experiments, using lasers to simulate microscopic warp bubbles, but we're light years from anything practical. There's also the problem of causality. Even if you could build a warp drive, accelerating beyond light speed relative to an outside observer might still create time paradoxes, like arriving at your destination before you left home. Some theorists suggest the bubble's walls could trap harmful radiation, turning your starship into a death trap of high-energy particles. Others worry that collapsing the warp field at your destination might unleash enough energy to sterilize a planet. Yet the allure persists. Breakthroughs in quantum vacuum physics or discoveries about dark energy, which already stretches space apart, could inch us closer. Imagine a future where humanity doesn't crawl between stars but glides on ripples of space-time itself. The Alcubierre drive reminds us that the universe's rulebook is stranger than we think, and the line between impossible and inevitable might just be a matter of perspective. After all, black holes were once mathematical oddities too, until we found them lurking in the dark. Who's to say warp bubbles won't be next? What if every attempt to change the past was doomed to fail, not by accident, but by the universe's ruthless enforcement of cosmic law? That's the spine-chilling premise of the Novikov self-consistency principle, a theory that reshapes time travel from a free-for-all into a straitjacket of inevitability. Proposed by Russian physicist Igor Novikov in the 1980s, the idea is deceptively simple. Any actions taken by a time traveler were always part of history, seamlessly woven into the timeline like invisible threads. Think of it as the universe's version of autocorrect. No matter how hard you try to create a paradox, reality bends to keep the story coherent. Take the classic grandfather paradox. You travel back to prevent your grandfather's meeting with your grandmother, ensuring your own birth never happens. Novikov's principle laughs at the attempt. Maybe your gun jams at the critical moment, or you miss the train to their hometown, or most unsettling of all, your interference causes their meeting, making you an unwitting pawn in your own existence. The universe isn't just resistant to paradoxes, it's obsessed with consistency, editing events on the fly to preserve cause and effect. It's as if time has an immune system, and paradoxes are the viruses it ruthlessly eliminates. This isn't just philosophical musing, it's grounded in hard physics. Novikov applied the mathematics of general relativity to show that closed time-like curves, the theoretical pathways allowing time travel, can only exist if they're self-consistent. Wormholes, rotating black holes, or other time-bending structures wouldn't just allow travel to the past, they'd constrain it, funneling events into a single, unchangeable sequence. Even your free will to alter things might be an illusion, with every choice you make in the past already accounted for in the timeline you remember. The implications ripple far beyond time machines. If Novikov is right, then the future might be as fixed as the past, not because destiny decrees it, but because any attempt to deviate would trigger forces we can't yet measure. Quantum experiments already hint at this. particles reacting to future measurements as if the outcome were predetermined. Some interpretations suggest that consciousness itself could be part of the mechanism, with observers unconsciously enforcing consistency by their very presence. But here's the twist that keeps physicists up at night. If the universe prevents paradoxes, does it also prevent change? Could every innovation, every rebellion against the status quo, be an illusion, just the universe playing out a script written in four-dimensional space-time? Or is self-consistency subtler, allowing for branching paths that feel like free will but ultimately converge? The answer might lie in the gray area between physics and philosophy, where the equations of relativity shake hands with the mysteries of human choice. One thing's certain, Novikov's principle doesn't just rule out chaotic time travel adventures, it redefines what possible even means. The past isn't a playground, it's a locked room, and every key you bring was always part of the lock. Whether that's comforting or terrifying depends on how much you trust the universe's editing skills. After all, if reality's already survived every time traveler's meddling, maybe we're exactly where we're meant to be, even if we'll never know who's pulling the strings. What if death isn't the end, just a doorway to another version of you, alive and unharmed in a parallel universe? The quantum suicide thought experiment takes the many worlds interpretation of quantum mechanics to its most chilling extreme. Picture this: you're sitting in a lab with a modified gun pointed at your head, rigged to a quantum particle in superposition. The trigger fires only if the particle collapses into a specific state, a 50-50 chance. If the many worlds theory is correct, every trigger pull splits reality. In one branch, the gun fires and you die, but in another, it doesn't and you live. Here's the twist: from your perspective, you'd never experience the fatal outcome, only the timelines where you survive. You'd watch the gun click harmlessly again and again, as if luck itself bends to keep you alive. This isn't just a macabre party trick, it's a razor-sharp test of quantum immortality. If consciousness truly branches with every quantum event, then death might be an illusion, a shadow that only falls on versions of you in other worlds. The experiment forces us to ask, is probability just a measure of our ignorance, or does the universe actively prune certain outcomes from our awareness? Some theorists argue that this could explain eerie near-death experiences, where people survive against impossible odds. Others point to the Fermi paradox, suggesting advanced civilizations might have tested quantum immortality to its limit, leaving behind empty universes where their luck finally ran out. But the implications go deeper than survival. If quantum immortality holds, it reshapes how we think about identity. Are you a single consciousness, or a thread woven through countless realities, snapping only when all possible paths lead to death? The thought experiment also exposes a flaw in how we perceive risk. Climbing Everest or skydiving might feel reckless, but if every dangerous act spawns branches where you make it, your subjective experience would always be the one where you succeed. It's a dangerous illusion, one that could tempt the reckless to push limits, believing the universe won't let them lose. Critics counter that quantum immortality is a misinterpretation. Consciousness doesn't hop between worlds but fragments into all possibilities, with no single version privileged. You don't cheat death, you simply exist in all outcomes, including the ones where you perish. And then there's the ethical quagmire. Even if the experiment worked, how could you ever prove it? The versions of you that die can't report back, leaving only survivors to wonder if they're lucky or locked in a cosmic loophole. Whether quantum immortality is profound truth or philosophical sleight of hand, it forces us to confront the fragility of existence. The universe might not guarantee life, but it certainly plays favorites, and the odds might be stranger than we ever imagined. So the next time you narrowly avoid disaster, ask yourself, did luck save you, or did the multiverse simply edit out the alternative? The answer could rewrite what it means to be alive or to die. The Big Bang wasn't the beginning, it might have been a cosmic encore. That's the radical proposition at the heart of Roger Penrose's conformal cyclic cosmology, a theory that rewinds the tape of time to ask, what if our universe is just the latest act in an infinite cycle of death and rebirth? Penrose, the Nobel-winning physicist who helped pioneer black hole mathematics, sees evidence of this eternal return etched in the sky itself, his controversial claim. Faint concentric rings in the cosmic microwave background, the afterglow of the Big Bang, are gravitational shockwaves from black hole collisions in a previous universe, imprinted like ghostly fingerprints on our own. This vision hinges on a mind-bending symmetry. As the universe expands toward heat death, all matter eventually decays into radiation, and black holes evaporate via Hawking radiation. At this point, space becomes so vast and empty that it loses any sense of scale, a state called conformal invariance. To a hypothetical observer, the cold, featureless end of one universe would be indistinguishable from the hot, dense singularity of the next. Like a phoenix dissolving into smoke only to reform from ashes, the cosmos resets, birthing a new Big Bang from the ashes of the old. The real bombshell is Penrose's purported evidence. Using data from the Planck satellite, he and colleagues identified anomalous rings in the CMB where temperatures vary in precise circular patterns, exactly what you'd expect if supermassive black holes from a prior eon had collided, sending gravity waves rippling through the void to imprint on the next cycle's birth. Skeptics counter that these patterns could be statistical noise or artifacts of data processing, but Penrose insists the odds of them appearing by chance are astronomically low. Not everyone's convinced. Rival theories like loop quantum cosmology propose a gentler rebound, where quantum effects prevent true singularities, causing the universe to bounce instead of tearing apart. Others argue that without a mechanism to transfer information between cycles, conformal cyclic cosmology is just poetic symmetry. Yet the allure remains. If Penrose is right, then every particle in your body carries echoes of infinite past universes, each with its own laws, stars, and perhaps even life, a chain of existence stretching backward forever. The stakes couldn't be higher. If cyclic models hold, the Big Bang wasn't a beginning but a transition, and the universe's fate isn't cold oblivion but eternal renewal. It's a vision that marries the grandeur of mythology with the rigor of mathematics, suggesting that time itself might be a circle we're only beginning to trace. And at the center of that circle, a mystery so profound it makes the Big Bang look like a single note in an endless cosmic symphony. The universe is expanding, galaxies drifting apart like leaves on a river, except for one eerie group that seems to be rowing against the cosmic current. Astronomers call this phenomenon dark flow, hundreds of galaxy clusters hurtling in the same direction at breakneck speeds, as if pulled by an invisible hand beyond the edge of everything we can see. It's not gravity from anything in our universe. The sheer scale rules out known superclusters. So what's tugging them? One spine-tingling possibility is that we're feeling the gravitational fingerprint of another universe entirely, a neighboring cosmos brushing against ours in the vast multidimensional landscape. The evidence comes from meticulous studies of the cosmic microwave background, the afterglow of the Big Bang. By tracking how galaxy clusters distort this faint radiation, a phenomenon called the kinematic Sunyaev-Zeldovich effect, researchers spotted the telltale motion. These clusters aren't just drifting randomly, they're racing toward a patch of sky near the constellations Centaurus and Vela at speeds exceeding 2 million miles per hour. The kicker, whatever's pulling them lies beyond the observable universe's horizon, tens of billions of light years away. That's like feeling a breeze from a hurricane that hasn't formed yet. Some theorists propose a jaw-dropping explanation. Our universe might be one bubble in a frothing multiverse, and these clusters are caught in the gravitational undertow of a nearby bubble. Picture two soap bubbles floating close together on a breeze. Their surfaces would subtly tug at each other even without touching. If another universe exists mere inches away in higher dimensional space, but trillions of light years distant in our three dimensions, its gravity could leak through, nudging our galaxies like a magnet tugging iron filings. String theory even provides a potential mechanism: giant cosmic strings, defects in space-time left over from the Big Bang, could stretch between universes, transmitting gravitational influence like puppet strings. Skeptics counter that dark flow might be an illusion, a statistical fluke or systematic error in interpreting CMB data. Others suggest less exotic but still wild causes. Perhaps a supermassive black hole from an earlier cosmic epoch was ejected during the Big Bang's turbulence, sailing beyond our observational limits but still dragging matter in its wake. Or maybe dark energy, the mysterious force accelerating the universe's expansion, isn't uniform but lumpy, creating gravitational tides we've yet to map. Yet the multiverse angle lingers because it solves a deeper puzzle: the uncanny fine-tuning of our universe's constants. If countless universes exist with random physical laws, ours might be one of the rare habitable ones, nestled close enough to others to feel their pull. Future telescopes like the European Space Agency's Euclid mission could settle the debate by mapping dark flow's reach with unprecedented precision. Until then, the mystery stands as a tantalizing hint that reality might be vaster, stranger, and more interconnected than we ever imagined. The next time you gaze at the night sky, remember, the cosmos isn't just expanding, it might be reaching towards something we can't yet see. The universe loves chaos. That's the unshakable law of entropy, where everything from shattered glass to dying stars trends toward disorder. But what if our entire reality, with its galaxies, planets, and even your memories of reading this sentence, is just a fleeting exception to that rule? This is the Boltzmann universe scenario, a thought experiment so unsettling it turns the cosmos into a cosmic roll of the dice. Picture a box of gas where atoms jitter randomly. Given enough time, those particles will occasionally arrange themselves into improbable patterns, like all gathering in one corner. Now scale that up to the universe. If entropy always increases, then statistically, an infinitely old cosmos should spend almost all its time in maximum chaos, a featureless soup of particles. The fact that we find ourselves in a pocket of staggering order, with structured galaxies and conscious life, might mean we're the equivalent of a winning lottery ticket drawn at random and destined to dissolve back into the void. Why doesn't this feel like a fluke? Here's where time's arrow sharpens the paradox. We remember the past but not the future because entropy increases in one direction, creating a gradient from order to disorder. But if the universe is just a random low-entropy bubble, there's no reason time should feel linear at all. You might suddenly find yourself remembering tomorrow while forgetting yesterday, or witnessing shattered teacups reassembling as entropy temporarily reverses. The fact that we experience time consistently suggests something deeper is at work, perhaps a fundamental asymmetry in the Big Bang's initial conditions, or a hidden law that privileges certain low-entropy states. Some physicists counter that the Boltzmann scenario is a statistical sleight of hand. If our universe were a random fluctuation, we'd expect it to be as small and minimal as possible, just a single brain floating in the void, hallucinating complexity. The vastness we observe, with its billions of galaxies, makes far more sense if our low entropy state has a physical cause, like cosmic inflation's explosive smoothing of spacetime. Others propose that consciousness itself might be the filter, selecting for coherent experiences in a sea of chaos. You don't perceive the disordered universes because there's no you there to witness them. Yet the idea lingers like a shadow. If the Boltzmann universe is possible, then every moment of order, every sunset, every thought, every atom in your body is a defiance of the cosmos' default state. It's a reminder that existence might not just be rare but precarious, balanced on a knife's edge between structure and dissolution. So the next time you watch steam rise from your coffee, remember, the universe prefers that swirling chaos. The fact that it allows islands of order at all might be the greatest mystery of all. What if the universe's most mysterious phenomena, wormholes and quantum entanglement, aren't just related, but secretly the same thing? That's the audacious claim of the EPR conjecture, a theory so elegant it could rewrite our understanding of space-time itself. Let's break it down. Refers to Einstein-Rosen bridges, the formal name for wormholes, those cosmic shortcuts threading through folded space. EPR stands for Einstein-Podolsky-Rosen, the trio who first described quantum entanglement's spooky action at a distance. At first glance, these ideas seem worlds apart. Wormholes are gravity's wildest architecture, while entanglement is quantum mechanics' most baffling quirk. But what if they're two sides of the same coin? Picture a pair of entangled particles as the mouths of a microscopic wormhole, their connection not just metaphysical but geometric, a tiny tunnel in the fabric of reality itself. This isn't just poetic analogy. The math suggests that when particles entangle, they might be forging Planck-scale wormholes too small to see, stitching space-time together with invisible quantum threads. Think of it like this: if you could zoom in on an entangled pair, you'd find not empty space but a labyrinth of microscopic bridges, each a twist in space-time's weave. This would mean entanglement isn't just a weird quantum quirk, it's the glue holding the universe's geometry together. The implications explode from there. Black holes, those infamous information shredders, might be entangled with their own Hawking radiation through a network of wormholes, preserving data we once thought lost. Even the Big Bang could have left behind a universe-scale web of these quantum tunnels, a hidden infrastructure we're only now learning to map. Now, imagine harnessing this for a quantum internet. Today's quantum computers rely on fragile entangled states to perform calculations. But if those states are secretly wormholes, we might one day engineer them into stable channels for instant communication, not by sending signals through space, but by exploiting the space-time shortcuts already woven into reality. It's like discovering your phone wasn't just making calls but tapping into a pre-existing subway system beneath the city. The catch: these wormholes would be ephemeral, snapping shut unless stabilized by negative energy, a hurdle that makes building a quantum web sound like trying to knit with spider silk. Yet the boldest implication isn't technological, it's metaphysical. If ER equals EPR, then space-time isn't the stage physics happens on. It's the emergent result of quantum relationships. The distance between stars, the span of your outstretched hand, even the gap between past and future might all be illusions, woven from deeper quantum connections we're only beginning to trace. It's a vision of reality where the universe isn't just stranger than we imagined. It's stranger than we can imagine, a tapestry where every thread is both a particle and a portal, and the act of looking might be what pulls them tight. If we're living in an advanced civilization simulation, why would they bother recreating their own past? It's one thing to imagine a hyper-realistic virtual world, But why simulate the struggles of ancestors who lacked interstellar travel, quantum computing, or even electricity? One unsettling answer is that we might not be the main characters in this digital universe. Instead, we could be non-playable characters NPC filling out the background of someone else's entertainment. Picture a next-generation video game where every blade of grass, every passerby on the street, has its own rich inner life, completely unaware it's just set dressing for the player's grand adventure. But historical research offers a more benevolent possibility. Advanced civilizations might simulate their past to study unrecorded eras, testing sociological theories or tracing the ripple effects of long-forgotten decisions. Imagine scholars in the year 1,000,000 running countless simulations of the 21st century, tweaking variables to see how climate change unfolds under different policies, or whether a single assassination could alter the course of world wars. In this view, we're not just code, we're live-action experiments, each simulation a petri dish for cosmic anthropologists. Then there's the darkest take, punishment. Some theorists speculate that simulated worlds could be ethical prisons, where consciousness is uploaded to atone for crimes in the base reality. Your daily commute, your struggles, even your heartbreaks might be part of an elaborate rehabilitation program or eternal confinement. It's a modern twist on ancient ideas of purgatory, with algorithms replacing divine judgment. Yet the most haunting question isn't why they'd simulate us, it's how we'd ever know. If the simulation is flawless, glitches might be intentionally rare or disguised as supernatural events to maintain immersion. Even our attempts to test the hypothesis could be part of the script, like a character in a novel pondering whether they're fictional. The simulation argument doesn't just challenge reality, it turns skepticism into a hall of mirrors where every doubt might be programmed. Whether we're someone's history project, entertainment, or something stranger, the ancestor problem forces us to confront the ethics of creation. If future humans could simulate conscious beings, would it be moral to do so? And if not, why would our creators be any different? The answer might determine whether we're living in a utopia's museum or a dystopia's theme park. Either way, the universe just got a lot more complicated. Black holes aren't just cosmic vacuum cleaners. They might be the ultimate gated communities for civilizations far beyond our imagination. Picture this, a super-advanced alien species, having mastered physics we're only starting to glimpse, chooses not to live around a black hole, but deep inside its event horizon. At first glance, that sounds like suicide once you cross that boundary. Even light can't escape. But here's the twist, certain black holes, particularly those that are large and rotating, might contain regions where the chaos of the singularity isn't an immediate death sentence. Instead, the interior could harbor hidden pockets of stability, even planets suspended in bizarre orbits where time and space twist into survivable configurations. How could this possibly work? Think of a spinning black hole like a whirlpool in space-time. As it rotates, it drags the fabric of the universe around it, a phenomenon called frame dragging, creating a zone just inside the event horizon where centrifugal force counteracts the crushing gravity. In this region, known as the ergosphere, objects might theoretically orbit without being instantly shredded. Some calculations even suggest the existence of closed time-like curves, loops where time circles back on itself, offering a stable, if surreal, environment for life. For a civilization capable of harnessing such forces, a black hole wouldn't be a prison, it'd be a fortress, a near-infinite energy source, and possibly the ultimate defense against cosmic threats. Energy extraction would be the key. The Penrose process, a real theoretical mechanism, allows energy to be siphoned from a black hole's rotation. Imagine a species building Dyson-like structures not around stars, but around the event horizon itself, capturing the unimaginable power of space-time itself being twisted apart. The energy output could dwarf anything a star could provide, making black holes the galactic equivalent of a supercharged battery. And if you're worried about the heat and radiation, advanced civilizations might use quantum field manipulation or exotic matter to create insulation, turning the black hole's fury into a controlled power grid. But what would life look like in such a place? Forget the humanoid aliens of sci-fi. These beings might be post-biological, their minds encoded in plasma clouds or quantum fields, perfectly adapted to the extreme physics of their home. Their perception of time could be radically different. Near the event horizon, time slows to a crawl relative to the outside universe. To them, 1,000,000 years of cosmic history might pass in what feels like minutes, letting them witness the birth and death of galaxies as fleeting moments. Communication with such civilizations would be nearly impossible for us, not just because of the physical barriers, but because their very concepts of reality might be as alien as their location. The wildest idea, black hole interiors might not just host life, they could create it. The intense gravitational energies near the singularity could spawn exotic particles and complex quantum states we can't yet imagine, forming the building blocks for entirely new forms of biology. Some theories even propose that black holes could contain universes within universes, with their own physical laws, meaning life inside might not just be adapted to extremes, but living in a reality fundamentally different from our own. Of course, this is all speculative. No probe we've ever sent could survive a black hole's interior, and our equations break down at the singularity. But that's the point. If a civilization has mastered physics beyond our comprehension, the rules we think are absolute might just be suggestions. Black holes could be the dark cities of the cosmos, teeming with life we're incapable of detecting, let alone understanding. And that raises a chilling question. If the universe's most advanced beings are hiding in plain sight, inside what we thought were cosmic graves, how would we ever know? The answer might not lie in looking for their signals, but in rethinking where and what life could even be. The idea that the universe might be trapped in an endless loop of expansion and collapse is both mesmerizing and terrifying. Imagine a cosmic heartbeat, each big bang followed by a big crunch, over and over, like a celestial accordion playing the same melody for eternity. This oscillating model offers a tantalizing escape from the bleak fate of heat death, where the universe fades into a cold, lifeless void. Instead, it proposes a universe that never truly dies, but rather resets, like a phoenix perpetually rising from its own ashes. But here's where things get eerie. If time itself is cyclical, are we doomed to relive the same existence in every iteration? Or does each cycle rewrite the script, offering infinite variations of reality? Think of it like a deck of cards being shuffled. If the universe collapses and rebounds with identical initial conditions, every cycle would play out exactly the same. Your birth, your thoughts, even this moment of reading these words would repeat without deviation. You'd never know because each cycle would erase the memory of the last. It's a haunting thought. The life you're living now might be the 10,000th performance of the same cosmic play, with no encores, no changes, just an endless rerun. But what if the shuffle isn't perfect? If quantum fluctuations introduce even the tiniest variations during the rebound, each cycle could spawn entirely new possibilities, alternate histories, different civilizations, or even laws of physics that shift subtly with each rebirth. The math behind this isn't just speculative. Einstein's equations allow for a closed universe where gravity eventually halts expansion and pulls everything back into a singularity. Some string theory models even suggest that the Big Bang itself could have been the rebound of a previous collapse, with quantum tunneling bridging the gap between cycles. The cosmic microwave background, that faint echo of the Big Bang, might hold clues anomalies in its pattern could be scars from a prior universe's death throes, like wrinkles in a recycled sheet of spacetime. But the most unsettling question isn't about mechanics, it's about meaning. If the universe is cyclical, does anything we do truly matter, or are we just transient actors in a show that's been staged countless times before? Philosophers have wrestled with this for centuries, but modern physics gives it new urgency. Maybe the answer lies in the fine print of entropy. If each cycle preserves some quantum information like a cosmic baton passed between iterations, then the universe isn't just mindlessly repeating, it's evolving, learning, or even remembering. Or perhaps the cycles aren't identical but fractal, each one a variation on a theme, with galaxies, stars, and life emerging in endlessly creative configurations. In that case, the universe becomes less like a broken record and more like an improv performance, where the same instruments play different songs every night. Either way, the idea of a time loop universe doesn't just challenge our place in the cosmos. It forces us to ask whether time itself is an illusion, a side effect of deeper, stranger rhythms we're only beginning to sense. And that's the real mystery, not just whether the universe repeats, but whether repetition is the exception or the rule. Every time you open your eyes, the world appears solid and predictable. Tables don't phase through walls, cats don't exist in two places at once, and your coffee cup stays firmly on the desk. But here's the paradox: at the quantum level, none of this should make sense. Particles exist in ghostly superpositions, capable of being everywhere and nowhere until observed. So why don't we see this chaos in our daily lives? Quantum Darwinism offers a startling answer. Reality isn't just there. It's selected through a survival of the fittest battle between quantum states, where the most stable configurations outcompete the rest to become what we call real. Think of it like a cosmic game of telephone. When a quantum system interacts with its environment, whether through light photons bouncing off an object or air molecules colliding with it, countless tiny measurements occur. Most quantum states cancel each other out or decohere into noise, but a handful prove resilient, replicating their information across the environment like a meme going viral. These robust states are the ones we perceive, while their fragile counterparts vanish into the background. Your desk appears solid not because it can't exist in a superposition, but because the solid desk state has been copied and reinforced by trillions of environmental interactions, drowning out the alternatives. This isn't just philosophy, it's a testable framework. Quantum Darwinism predicts that the fittest states leave measurable imprints in their surroundings. Experiments with nitrogen vacancy centers in diamonds have shown hints of this. When quantum systems are gently probed, certain states emerge as dominant, their information redundantly encoded in the environment. It's as if reality is a mosaic, and only the tiles sturdy enough to withstand constant scrutiny end up in the final picture. But the theory's real power lies in bridging two seemingly unrelated worlds, quantum mechanics and biology. Just as natural selection shapes life by preserving advantageous traits, quantum Darwinism suggests that the laws of physics select observable reality through environmental persistence. This could even explain why our brains evolved to perceive time, space, and objects the way we do. Those interpretations were the most stable, the most useful for survival in a quantum sea of possibilities. Critics argue the theory merely rebrands decoherence, the process where quantum weirdness fades as systems interact with their surroundings. Yet quantum Darwinism goes further, proposing that consensus reality emerges from information winning a competition, not just randomness. If proven, it would mean the universe isn't just probabilistic but adaptive, with observation acting as a filter that distills order from quantum soup. The implications ripple far beyond physics. If reality is shaped by what information survives, could other classical worlds exist where different states won the competition? Are there pockets of the universe where superpositions remain visible, like quantum islands in a sea of decoherence? And most hauntingly, if consciousness plays a role in selecting states, does that mean reality is, in some small way, a collaboration between observer and environment? For now, the theory remains a provocative lens, not proven fact, but it offers something rare, a plausible path from the subatomic fog to the sharp, shared world we all experience. The next time you reach for that coffee cup, remember, its solidity isn't just physics. It's the universe's most successful meme, echoing endlessly through the quantum noise until even the cosmos agrees this is real. What if gravity worked in reverse, not pulling you down, but pushing you skyward like an invisible trampoline? This isn't just a thought experiment. It's the bizarre reality of negative mass, a hypothetical form of matter that could hold the keys to warp drives, wormholes, and rewriting the rules of physics as we know them. Unlike antimatter, which still has positive mass, negative mass would defy Newton's most basic law. When pushed, it would accelerate toward the force instead of away, like a car that speeds up when you hit the brakes. Picture dropping a ball made of this stuff. It wouldn't fall to the ground. It'd rocket upward, gaining speed as if space itself were repelling it. The implications for space travel are staggering. Einstein's equations show that negative mass could theoretically stabilize wormholes, propping open their throats against collapse like an indestructible scaffold. Even more tantalizing is its role in the Alcubierre warp drive, where a shell of negative mass would compress space-time in front of a ship and expand it behind, creating a bubble that moves faster than light without breaking relativity. The catch, negative mass has never been observed in nature, but lab experiments are teasing the edges of possibility. In quantum fluids, certain conditions can create effective negative mass. When ultra-cold atoms are manipulated with lasers, they briefly behave as if they have negative inertia, flowing backward when nudged. It's not true negative mass, but it's a ghostly hint that the real thing might not be pure fantasy. Why does this defy intuition so violently? Because negative mass isn't just anti-gravity, it's anti-physics. If you tied a positive mass to a negative one, the pair would self-accelerate indefinitely, generating infinite energy from nothing. Push the positive mass forward, and the negative mass would pull it faster in the same direction, creating a runaway effect that violates conservation laws. Some theories sidestep this by requiring negative mass to always appear in balanced configurations, like dipoles where the chaos cancels out. Others propose it's locked away in higher dimensions or hidden inside black holes where its effects are contained. The biggest mystery isn't just whether negative mass exists, it's how it could exist without unraveling the universe. Quantum field theory allows for negative energy densities in fleeting bursts, like the Casimir effect's ghostly pull between metal plates. Could extended regions of negative mass emerge from similar quantum trickery, or is it forever out of reach, a mathematical quirk that reality forbids? For now, it remains a tantalizing what if, a reminder that the universe's rulebook might have pages we haven't even glimpsed yet, and if we ever find it. The stars wouldn't just be the limit, they'd be the starting line. Imagine a civilization so advanced it doesn't just harness the energy of a star, it cages it, wrapping its home sun in a vast lattice of solar panels like a celestial power plant. This is the Dyson sphere, a hypothetical megastructure that could be the ultimate signature of an alien society. Yet here's the puzzle. If these cosmic power grids exist, why does our sky look so empty? The answer might not be that we're alone, but that we've been searching for aliens in the wrong dimensions. Consider the scale of a Dyson sphere. To build one, a civilization would need to dismantle planets, forge materials stronger than anything we know, and orchestrate construction on a stellar scale. The energy output would be staggering, radiating waste heat detectable across galaxies, which is exactly how we've been hunting for them. For decades, SETI has scanned the cosmos for infrared anomalies, the telltale glow of a star wrapped in technology. But what if we're missing the obvious? A Dyson sphere built in 4 spatial dimensions wouldn't obscure its star in ways we can perceive. Like a shadow cast from a higher dimension, its structure might distort starlight in patterns our 3D telescopes can't decode. This isn't just about geometry, it's about strategy. Advanced civilizations might prioritize stealth, nesting their megastructures in dimensional folds to avoid cosmic threats. Picture an ant crawling on a sheet of paper, unaware of the library surrounding it. To the ant, a book placed vertically on the paper would appear suddenly, inexplicably. Similarly, a 4D Dyson sphere might intersect our 3D universe in fragments, appearing as transient anomalies, stars that flicker oddly or vanish without explanation. Some astronomers speculate that KIC 8,462,852, Tabby's star with its bizarre, irregular dimming, could be a Dyson artifact brushing against our plane of existence. But the paradox cuts deeper. Even if higher dimensions aren't the answer, our search methods might be laughably primitive. We assume aliens would convert starlight into heat waste, but what if they've mastered zero-point energy or quantum recycling, leaving no thermal trace? Or perhaps Dyson spheres aren't solid shells but swarms of nanoscale satellites, orbiting in formations too sparse for our telescopes to resolve, the darkest possibility. They've moved on. A civilization capable of building Dyson spheres might have already transcended physical stars, uploading their consciousness into black hole computers or digital universes, leaving behind skeletal megastructures as relics of a bygone era. The silence of the cosmos isn't just a mystery, it's a mirror. Every assumption we make about alien technology reflects the limits of our own imagination. If we ever do spot a Dyson sphere, it might not look like a construct of metal and glass, but like a glitch in the sky, a seam where reality itself has been folded. And that's the real lesson. The universe doesn't owe us legible blueprints. The answers are out there, but we might need to learn to see in more dimensions to find them. The moment you look away, does the moon cease to exist? This isn't just poetic musing, it's the spine of consciousness-created reality theory. A quantum interpretation so radical, it flips the universe from an objective stage to a collaborative hallucination. At the heart of this idea lies the observer effect, where quantum particles seem to snap from fuzzy probabilities to concrete states only when measured. But here's the twist. What counts as a measurement? If a tree falls in a quantum forest with no one to observe it, does it make a sound or even exist? Some interpretations, like von Neumann-Wigner consciousness hypothesis, argue that reality's final collapse requires a sentient mind, not cameras, not detectors, awareness itself. Consider Schrödinger's infamous cat, both dead and alive in its box until someone peeks inside. The Copenhagen interpretation treats this as a mathematical quirk, but consciousness-centric theories take it literally. Your observation isn't just recording reality, it's completing it, like a painter adding the final stroke that turns random colors into a landscape. proponents point to quantum experiments where particles appear to know future measurement choices, as if time bends to accommodate conscious intent. Even delayed choice experiments, where decisions made after a particle's journey alter its past behavior, suggest reality might be a tapestry woven in hindsight, with consciousness as the loom. But critics pounce on the slippery slope. If consciousness creates reality, why do we all agree on the moon's existence? Why don't light switches toggle randomly when no one's watching? Decoherence theory offers a counter. Interaction with the environment, air molecules, stray photons collapses quantum states mechanically, no mind required. Yet the hard problem of consciousness lingers. Why does subjective experience exist at all in a universe that could, in principle, run on autopilot? Some theorists split the difference, suggesting consciousness doesn't create reality but selects it from a quantum multiverse, like tuning a radio to one station while others play silently. The philosophical fallout is a minefield. If consciousness is fundamental, does that imply a cosmic mind underlying existence? Buddhist and Hindu philosophies have argued this for millennia. Modern physics might just be catching up. Or worse, does it trap us in solipsism, where you're the only real mind in a universe of NPCs? The theory's most pragmatic takeaway might be humility. Whether consciousness is the engine or a passenger, quantum mechanics has shattered the illusion of a detached, objective universe. Reality isn't something we find, it's something we participate in, moment by moment, observation by observation. And that changes everything. Black holes aren't just cosmic vacuum cleaners, they're also the universe's most efficient filing cabinets, storing information in a way that defies everything we know about space and memory. Here's the puzzle. According to the laws of thermodynamics, entropy, a measure of disorder, should scale with volume. The more space you have, the more ways things can get messy. But black holes flip this logic on its head. Their entropy doesn't depend on how much stuff you cram inside. It's determined by the surface area of their event horizons. It's like counting the number of books in a library, not by the shelves they fill, but by the titles etched on the front door. This bizarre discovery traces back to Jacob Bekenstein and Stephen Hawking in the 1970s. Hawking initially argued black holes couldn't have entropy. After all, they were supposed to be simple, swallowing everything without a trace. But Bekenstein noticed something eerie. When you toss an object into a black hole, the horizon's area increases, just as entropy should when you add disorder to a system. Hawking eventually conceded, deriving a formula showing a black hole's entropy is proportional to its event horizon's area divided by infinitesimally tiny Planck squares. The result, a stellar mass black hole's entropy dwarfs the combined entropy of every particle in the observable universe. That's not just a big number, it's a clue that black holes might be encoding information in ways we barely grasp. The real shocker came when theorists realized this isn't just a quirk. It's a signpost to quantum gravity. If entropy counts the number of microstates a system can have, then a black hole's surface area scaling suggests its innards are somehow projected onto its boundary like a hologram. This insight birthed the holographic principle, the idea that our three-dimensional reality might be a shadow cast by information stored on a distant two-dimensional surface. Think of it like a movie screen. The images seem three-dimensional, but all the data comes from flat pixels. Black holes could be the universe's way of showing us that space-time itself operates on similar rules. But how does this encoding actually work? String theorists propose that black hole horizons are tiled with Planck-sized bits, each storing quantum information in vibrating strings or entangled qubits. Others suggest the horizon acts like a quantum error-correcting code, scrambling data so thoroughly it becomes radiation when the black hole evaporates. The math gets wilder. Some equations imply that falling into a black hole doesn't destroy you. It pastes your quantum state onto the horizon while a scrambled copy burns up in the interior. It's as if the universe photocopies your existence, then shreds one version while preserving the other in cosmic latex. Why does this matter beyond theoretical gymnastics? Because if we crack how black holes store data, we might finally unite quantum mechanics and general relativity, the holy grail of modern physics. Every black hole could be a Rosetta Stone, its surface etched with the missing grammar of quantum gravity. And here's the kicker: if space-time itself is holographic, then black holes aren't exceptions, they're magnifying glasses, revealing the pixelated underpinnings of reality we're usually too small to see. The next time you gaze at the night sky, remember, the darkest spots might hold the brightest keys to the universe's deepest secrets. The gun clicks empty again. You pull the trigger a fifth time, then a sixth, your hands steady despite the chambered bullet that should have ended you. According to the rules of probability, this outcome is nearly impossible. Yet here you stand, unharmed, while somewhere in the quantum foam, other versions of you weren't so lucky. This is the chilling premise of quantum immortality, a thought experiment that takes the many worlds interpretation of quantum mechanics to its most unsettling extreme. If every possible outcome spawns a new universe, then statistically, there's always a branch where you survive, no matter how slim the odds. At first glance, it sounds like a cosmic safety net. Step in front of a speeding train, and while most versions of you perish, one inevitably dodges at the last second. But the devil's in the details. Survival doesn't mean unscathed. You might wake up in a hospital, paralyzed but alive, or trapped in a timeline where the train derailed, killing hundreds while you crawled from the wreckage. Quantum immortality doesn't guarantee a happy ending, just a conscious one. The longer you test it, the more your existence narrows to increasingly improbable, often horrifying scenarios. Imagine playing Russian roulette daily. After a year, you'd be the sole survivor in a sea of timelines where your body lies cold, your loved ones grieving in countless realities you'll never see. This isn't just philosophical speculation, it reshapes how we think about risk. Normally, we assume dangerous choices have consequences, but if quantum immortality holds, reckless behavior might not feel reckless subjectively. Your experience would always be the timeline where the free solo climb succeeded. The parachute opened, the bullet missed. The catch: you'd pay a psychological toll, living in a world where your survival borders on supernatural. Friends would call you unnaturally lucky. Statisticians would study you as an anomaly. And with each brush with death, the weight of your uniqueness would grow heavier, isolating you in a universe that seems to bend around your persistence. Critics argue the experiment misunderstands quantum branching. Consciousness doesn't hop between worlds, it fractures into all possibilities simultaneously. You don't cheat death, you merely inhabit the branches where death hasn't found you yet. Others point out that quantum effects rarely scale to macroscopic events like gun triggers or train collisions. But the thought experiment's power lies in its razor's edge question. If reality splits infinitely, does subjectivity become a prison, narrowing your perception to the single thread where you persist? The ethical implications are thornier still. If you believe in quantum immortality, would you take risks you'd otherwise avoid? Would societies collapse if everyone acted like protagonists in their own multiversal saga? The experiment doesn't just challenge physics, it probes the nature of sanity itself. After all, how would you know if you're truly invincible or just delusional, mistaking luck for cosmic favor? Perhaps the darkest twist is the experiment's unfalsifiability. The only way to lose is to die, but if you're right, you'll never experience that outcome. The paradox loops endlessly. Proof requires survival, and survival feels like proof. In the end, quantum immortality isn't a theory to test. It's a mirror reflecting our deepest fears about fate, free will, and the price of being the universe's favorite. Dark energy isn't just accelerating the universe's expansion. It might be the cosmos hitting its storage limit. Imagine your computer slowing to a crawl when the hard drive fills up, struggling to process new data. Now picture the universe itself behaving the same way, its mysterious dark energy acting like a cosmic, low-memory warning. This is the holographic dark energy model, a theory so audacious it treats space-time like a hard drive with finite space, where the energy driving galaxies apart emerges from the universe's informational constraints. At the heart of this idea lies a radical reimagining of gravity and entropy. Normally, we think of dark energy as a property of empty space, Einstein's cosmological constant, a static energy woven into the vacuum. But holographic dark energy suggests it's dynamic, tied to the surface area of the universe's horizon, the farthest distance light could have traveled since the Big Bang. As the universe expands, this horizon grows, increasing the maximum possible entropy, the number of bits needed to describe everything within it. Dark energy, in this view, isn't a force but a side effect, the universe's way of balancing its informational budget, like adjusting a thermostat when the room gets too crowded. The numbers line up eerily well. Quantum field theory predicts a vacuum energy density 120 orders of magnitude larger than what we observe, a discrepancy so vast it's called the worst prediction in physics. But if dark energy isn't intrinsic to space but emerges from holographic limits, its measured value fits neatly with the universe's current horizon size. It's as if the cosmos self-regulates, preventing its own informational overload by expanding just fast enough to keep the total entropy within bounds. Where things get truly wild is the computational metaphor. If the universe has finite information capacity, could it be processing reality like a quantum computer? Some theorists speculate that dark energy's acceleration might represent computational inefficiency, a growing lag as cosmic operations become more complex. Just as a computer heats up when pushed to its limits, the universe's expansion could be the thermodynamic cost of running the ultimate simulation. This isn't just poetic analogy, it's math. The holographic principle, born from black hole physics, suggests that all 3D reality might be projected from a 2D boundary, with dark energy as the tension between the projection and its source. Critics argue the model is too speculative, lacking a mechanism to explain how information limits translate to repulsive gravity. Yet it offers something rare, a solution to the why now problem. Dark energy's dominance coincides with the era when the universe's horizon size matches its informational capacity, a coincidence the holographic model explains naturally. It also dovetails with entropic gravity theories, where gravity itself emerges from statistical tendencies, not fundamental force. The implications ripple beyond cosmology. If holographic dark energy is real, it hints that spacetime is pixelated at the tiniest scales, with dark energy acting like the universe's way of defragmenting its storage. Future telescopes measuring the expansion rate with unprecedented precision could confirm or rule out this model. Until then, it stands as a haunting reminder. The universe might not just be expanding, it could be upgrading one cosmic byte at a time. Neutrinos are the universe's ultimate escape artists, slipping through planets like ghosts through walls, barely interacting with matter at all. But what if their elusiveness isn't their only trick? These subatomic particles, born in the hearts of stars and supernova, travel so close to the speed of light that relativity warps their experience of time. For a neutrino, a cross-galaxy journey might feel like seconds while centuries pass for us. This time dilation effect isn't just a quirk, it's the backbone of the neutrino time travel hypothesis, a wild yet mathematically sound idea that these particles might not just traverse space but time itself. The theory hinges on Einstein's revelation that time slows for objects approaching light speed. Neutrinos, which can reach 99.9999% of that velocity, experience time drastically slower than we do. If one could somehow be encoded with information, perhaps by an advanced civilization, it might arrive at Earth carrying data from what to us is the distant future. Imagine a neutrino broadcast sent from a star system 10,000 years ahead of us, its message riding the edge of causality to whisper secrets from tomorrow. It sounds like science fiction, but the math doesn't rule it out. In fact, certain solutions to quantum field equations allow for retrocausality, where effects precede causes on microscopic scales. If neutrinos exploit these loopholes, they could be nature's own time capsules. The real challenge is detection. Neutrinos are infamous for their reluctance to interact. Trillions pass through your body every second without a trace. Catching one is hard enough. Decoding a potential message is like trying to read a book by listening to the sound of its pages turning in a hurricane. Yet experiments like IceCube in Antarctica and Japan's Super Kamiok are making progress, spotting high-energy neutrinos from cosmic cataclysms billions of light-years away. If these particles were engineered as carriers, their messages might be hidden in subtle patterns, timing delays, energy fluctuations, or even quantum entanglement links with other neutrinos. Skeptics argue that even if neutrinos could carry time-shifted signals, the energy required to encode them would be astronomical. Others point out that time dilation only sends particles forward from their own perspective, not backward to our past. But here's where quantum weirdness creeps in. Some interpretations of quantum mechanics suggest that entangled neutrinos could share correlations that appear to transcend time, creating a bridge between cause and effect that defies linear logic. It's not quite messages from the future, but it's close enough to make physicists pause. The most tantalizing possibility: we might have already received these signals without realizing it. Anomalous neutrino bursts like those detected from Blazar TXS 0506 plus 056 in 2017 could be more than cosmic accidents. They might be fragments of a larger puzzle, a galactic Morse code we're only beginning to decipher. Whether the neutrino time travel hypothesis holds up or not, it forces us to confront a humbling truth. The universe's smallest messengers might be carrying its biggest secrets, and we've only just started listening. Black holes aren't cosmic dead ends, they might be cosmic rebirths. Imagine the crushing weight of a collapsing star not as a final implosion, but as a cosmic trampoline where matter rebounds into an entirely new universe. This is the Planck star hypothesis, a radical idea born from loop quantum gravity, a theory that reimagines space-time as a woven fabric of indivisible threads. At the black hole's core, instead of a singularity, a point of infinite density where physics breaks down, there's a fleeting, ultra-dense object no bigger than a Planck length, the smallest possible unit of space. This Planck star doesn't vanish into oblivion. It bounces, triggering a new Big Bang and birthing a fresh cosmos inside the black hole's depths. The math behind this is as elegant as it is mind-bending. Loop quantum gravity suggests space-time isn't smooth and continuous but pixelated, like a digital image. When gravity tries to squeeze matter beyond the Planck scale, these quantum pixels resist, creating a repulsive force so powerful it halts collapse and reverses it. Picture a spring compressed to its limit. The harder you push, the fiercer it fights back. In this scenario, the black hole's interior becomes a pressure cooker where space-time itself recoils, exploding outward in a fireball of energy, a new universe expanding where the old one seemingly ended. What makes this more than just theoretical poetry? The echoes we might detect. If our own universe began as a Planck star rebound, the violent birth could have left scars in the cosmic microwave background, subtle swirls or temperature variations that telescopes like the James Webb might one day spot. Even wilder, if black holes are cosmic matryoshka dolls, each nesting a new universe inside, then our entire reality could be the interior of a black hole from a parent cosmos. The laws of physics we hold sacred might just be local bylaws inherited from the specific conditions of our black hole's bounds. Critics argue Planck stars are speculative, lacking direct evidence. Yet they solve two colossal puzzles at once. First, the singularity problem, no more infinities, just a quantum rebound. Second, the Big Bang's origin, no need for a mysterious before. Time could loop eternally, with each collapse seeding a new expansion. The theory even hints at dark matter's nature, leftover remnants from previous cycles, floating like cosmic breadcrumbs from universes past. The most profound implication: black holes aren't tombs, they're wombs. Every galaxy's heart might harbor not just a monster, but a mother, a Planck star quietly nurturing the seeds of the next cosmos. And if that's true, our universe's fate might not be heat death, but rebirth, as some future black hole's collapse sparks a chain reaction of cosmic regeneration. The night sky's darkest voids could be the very cradles of existence, turning death into the engine of creation itself. Time feels like a river carrying us from past to future, but what if that's just the current's illusion? Einstein's theory of relativity shattered the notion of a universal now, revealing that time flows differently depending on speed and gravity. Yet the block universe theory takes this further, proposing that past, present, and future aren't sequential at all. They exist simultaneously, frozen in a four-dimensional tapestry where every moment from the Big Bang to the death of the last star is equally real. Your childhood, this exact second, and every tomorrow you'll ever experience might already be out there, fixed in place like frames in a cosmic film reel. This isn't just philosophical speculation, it's embedded in the math. Einstein's equations treat time as a dimension akin to space, where before and after are coordinates, not transitions. Picture a loaf of bread. Slicing it crosswise gives you now, but the entire loaf exists at once. In this view, the flow of time is a trick of perception, a glitch in how consciousness navigates the block. Quantum experiments add fuel to the fire. Entangled particles seem to ignore temporal order, with measurements affecting each other backward in time, as if the universe doesn't care which frame we call past or future. But if time is static, why does life feel so dynamic? The omnipresent present theory suggests that consciousness itself might be the projector, stitching together moments into a coherent narrative. Think of a film strip. The images are all there, but only light and motion create the illusion of a story. Our brains could work similarly, constructing the sensation of flow from static slices of spacetime. This idea finds eerie parallels in neuroscience. Patients under certain anesthetics report timeless states, and déjà vu might be moments where the brain's temporal stitching falters, revealing the block seams. Critics argue this reduces free will to an illusion. If the future's already written, are choices just shadows cast by predetermined events? Not necessarily. Some interpretations of quantum mechanics suggest every possible decision branches into parallel blocks, creating a multiverse of frozen timelines. Others propose that consciousness isn't trapped in the block but interacts with it, selecting paths like a reader choosing which sentence to focus on next. The most haunting implication: if the block is real, then grief and nostalgia take on new dimensions. Lost loved ones aren't gone, they're still there in their slice of space-time, as real as you are in yours. The future's joys and tragedies likewise persist, waiting like unopened letters. This doesn't erase life's urgency, it reframes it. Every moment isn't a fleeting whisper, it's a permanent chord in the universe's symphony, echoing forever in the structure of reality itself. The next time you check your watch, remember, the hands aren't moving forward, they're just pointing to where you are. From holographic codes to time loops, these 36 concepts don't just bend the rules, they shatter our understanding of reality itself. Whether it's black holes birthing universes or quantum particles whispering across time, each idea forces us to confront how little we truly grasp about the cosmos. Some might sound like pure science fiction, but remember, black holes were once dismissed as mathematical oddities until we captured one's shadow with a telescope the size of the Earth. The line between speculation and discovery has always been thinner than we think. Take holographic reality. What seems like a wild thought experiment could one day explain why the universe's information fits perfectly on its boundary, like a cosmic zip file. Or consider the Boltzmann brain paradox, where your consciousness might just be a fleeting fluctuation in an otherwise chaotic void. These aren't just brain teasers, they're stress tests for our best theories, revealing cracks in our understanding that could lead to the next physics revolution. And let's not forget the practical implications. If entanglement really is a hidden network of wormholes, as the AR equals EPR conjecture suggests, we might be on the brink of unlocking instantaneous communication, or even rewriting the rules of space travel. Time crystals, once deemed impossible, are now pulsing in labs, hinting at materials that could revolutionize quantum computing. The most outlandish ideas today could be tomorrow's textbooks. But here's the real magic. These concepts don't just belong to physicists. They invite all of us to play with the universe's deepest mysteries. Maybe you're captivated by the simulation hypothesis, wondering if glitches in reality could reveal the code beneath. Or perhaps the block universe's frozen time speaks to you, turning life into a mosaic where every moment exists forever. That's the beauty of this journey. No single answer, just endless questions waiting to be explored. So which idea rewired your brain? Drop your favorite in the comments. We're all cosmic detectives here, piecing together clues from the quantum to the galactic. And if this deep dive left you hungry for more, hit subscribe so you never miss our next adventure into the unknown. The universe is stranger than fiction, and the next breakthrough might be just one thought experiment away. Until then, stay curious, stay bold, and never stop asking. What if these ideas have ignited your curiosity like a supernova, you're not alone, and the journey doesn't end here? For those hungry to dive deeper, let's talk tools. Start with Brian Greene's The Hidden Reality, a book that unpacks multiverses and higher dimensions with the clarity of a master storyteller. Greene doesn't just explain the science, he makes you feel it, weaving relatable analogies about cosmic wallpaper patterns and universe-sized loaves of bread. Or grab Black Hole Blues by Janna Levin, which reads like a thriller about the decades-long hunt for gravitational waves, proving real-life science is every bit as dramatic as fiction. Prefer visuals? The PBS series The Fabric of the Cosmos is your gateway, blending CGI and cutting-edge experiments to show how space-time warps like rubber. For something more immersive, A Trip to Infinity on Netflix tackles the mind-bending mathematics of the infinite with animations that'll make your head spin in the best way. And don't overlook YouTube gems like PBS Space-Time or Veritasium. where experts break down everything from quantum entanglement to dark flow in digestible, binge-worthy chunks. But why just watch when you can participate? Platforms like Zooniverse let you sift through telescope data to spot undiscovered galaxies or classify gravitational wave signals. It's like being handed the keys to the universe's backroom, no PhD required. If you're craving human connection, local astronomy clubs are treasure troves of passionate debaters. Picture this, a room full of strangers arguing over whether the holographic principle explains consciousness, fueled by nothing but coffee and cosmic wonder. Online, forums like the Physics Stack Exchange or Reddit's r/Cosmology turn these theories into living conversations, where a casual comment might spark a revelation. The most thrilling part, we're all detectives in this grand cosmic mystery. Every book you read, every documentary you watch, every dataset you analyze adds another piece to the puzzle. Who knows, your curiosity might one day uncover a glitch in the simulation or a pattern in the CMB that rewrites textbooks. The universe isn't just out there, it's waiting for you to reach back. So grab a telescope, a notebook, or just your imagination. Adventure doesn't get bigger